Now we are going to discuss history and various types of pavements. History. In its most general sense, a road is an open, generally public way for the passage of vehicles, people, and animals. The earliest human road builders predate recorded history by thousands of years. With the advent of modern man road building, the purposeful construction of general public ways became a common sign of an advancing civilization. Covering these roads with a hard, smooth surface helped make them durable and able to withstand traffic and the environment. Some of the oldest paved roads still in existence were built by the Roman Empire. So look at the Roman roads. So this is the Roman road. By and large, Roman roads were constructed during the Republican times. The oldest road, via Pia, dates back to 312 BC before Christ. The Roman road network consisted of over 100,000 kilometers or 62,000 miles of roads. The superior quality and structure of its pavement have allowed many Roman roads to survive to this day. Here this is the cross section of a typical Roman road, and these are the different layers, and the description about these layers is given on this slide. So the topmost layer, that is the summa crusta, that is the surfacing, smooth polygonal blocks embedded in the underlying layer. Nucleus, a kind of base layer composed of gravel and sand with lime or cement. Rudus, the third layer, was composed of rubble masonry and smaller stones also set in the lime mortar. Stadtman, 2 or 3 courses of flat rubble stones set in lime mortar. Telford Pavements. The first insight into today's modern pavements can be seen in the pavements of Thomas Telford. Telford served as a building mason and extended his masonry knowledge to bridge building. During lean times, he carved gravestones and other ornamental work. Eventually, Telford became the surveyor of public works for the county of Thalop, thus turning his attention more to roads. Telford attempted, where possible, to build roads on relatively flat grades, no more than a 1 in 30 slope, in order to reduce the number of horses needed to haul cargo. Telford's pavement section was about 350 to 450 mm or 14 to 18 inches in depth and generally specified 3 layers. The bottom layer was comprised of large stones, 100 mm or 4 inches wide and 75 to 180 mm, 3 to 7 inches in depth. It is this specific layer which makes the Telford design unique. On top of this were placed 2 layers of stones of 65 mm or 2.5 inches maximum size, about 150 to 250 mm or 6 to 9 inches total thickness, followed by a varying course of gravel about 40 mm, 1.6 inches thick. It was estimated that this system would support a load corresponding to about 88 Newton per millimeter, or 500 pounds per inch of width. So this is the typical cross section of the Telford pavement. So these are the layers, different layers that you can see. Then comes the Macadam pavements. Macadam pavements introduced the use of angular aggregates. John Macadam observed that most of the paved United Kingdom roads in early the 1800s were composed of rounded gravel. He knew that angular aggregate over a well-compacted subgrade would perform substantially better. He used a sloped subgrade surface to improve drainage, unlike Telford, who used a flat subgrade surface, on which he placed angular aggregate, hand broken with a maximum size of 75 mm or 3 inches, in 2 layers for a total depth of about 200 mm or 8 inches. On top of this, the wearing course was placed about 50 mm thick with a maximum aggregate size of 25 mm. Macadam's reason for 25 mm, that is 1 inch maximum aggregate size, was to provide a smooth ride for wagon wheels. The total depth of a typical macadam pavement was about 250 mm, that is 10 inches. Macadam was quoted as saying, "No stone larger than will enter a man's mouth should go into a road." The largest permissible load for this type of design has been estimated to be 158 Newton per millimeter or 900 pounds per inch width. In 1815, Macadam was appointed Surveyor General of the Bristol roads and was then able to use this design on numerous projects. It proved successful enough that the term macadamized became a term for this type of pavement design and construction. The term macadam is also used to indicate broken stone pavement. So this is the cross section of the macadam pavement. Now we are having the modern highways like that. Pavement overview. If you just look at the pavement purpose, typically pavements are built for 3 main purposes: load support, smoothness, and drainage. So load support means the pavement material is generally stiffer than the material upon which it is placed. Thus, it assists the in situ material in resisting loads without excessive deformation or cracking. Smoothness. Pavement material can be placed and maintained much smoother than in situ material. This helps improve ride comfort and reduce vehicle operating costs. Drainage. Pavement material and geometric design can affect quick and efficient drainage, thus eliminating moisture problems such as mud and ponding puddles. So, what is a pavement? The answer is a multi-layer system that distributes the vehicular loads over a larger area. So here you can see the different layers of this road, and this is the wheel that is going to move on that particular road. And in this way we are having the distribution of this wheel load. Classification of pavements. Classification by function, we are having the airport pavements, highway and freeway pavements, parking and street pavements. And if we just consider the structure, on the basis of structure we are having the classes like rigid or concrete pavements, flexible pavements or asphalt concrete pavements, composite pavements, and then another category that is the gravel pavements, that means unpaved pavements. So rigid pavement and the flexible pavement, these two pavements are not new, we have already discussed, but this is the new one, the composite pavement, and we will discuss this one in today's lecture. So here you can see the flexible pavement and you can see the conventional components. So subgrade upon subgrade we are having the subbase, upon that we are having the base course, and this is the surfacing. And you can see that this one is the binder course, intermediate or binder course, and this is the wearing course. And look at this one. The prime coat of bitumen has been provided in between the binder course and the base course. And if you just look at this one, where I am moving this pointer, you can see that this is the tack coat, and this tack coat is provided to develop a bond between the wearing course and the binder course. And at the top we have got the seal coat just to seal the surface of the wearing course. So conventional components of flexible pavement you can see in this particular diagram. Now flexible pavement structure, typical flexible pavement structure. So here this green color, and it is meant for the flexible pavement. So you can see here the cross section above the subgrade subbase, above that base course, and then at the top we are having the surface course, or simply you can say surfacing. So in the surfacing we can have the proper asphalt concrete, or we can have the surface treatment. But this surface treatment is of low quality, and when you are using the asphalt concrete, it means the surfacing is of high quality. Now in this particular slide, green color is meant for rigid. So this is the typical cross section for the rigid pavement. Upon subgrade we are having the base or the leveling course, and above that you can see the PCC slab has been placed, and joints are to be provided, and at the joints steel will be provided. And this is a composite pavement. In fact, you can say that it is something, you can say the combination of the flexible and the rigid pavement. So in this particular case, you can see that subgrade, base course, and the PCC surface. So up till now we are having the rigid pavement, and upon that you can see the asphalt concrete layer has been provided. So this structure is basically the composite pavement structure. So composite pavements are of two types. Number one, the composite pavement black topping. So here the idea is that actually we are having the rigid pavement, and upon that we have provided the leveling course, and above the leveling course we have just provided the asphalt concrete overlay. So this is the composite pavement, or simply you can say the black topping pavement, because if you just look at the color of asphalt, it is very dark brown to black color, so that's why it is called as the black topping. On the other hand, if you just look at this case, that is the second type of the composite pavement, that is the white topping. So originally we had the flexible pavement over here. At the top of that we provided the leveling course, and then the PCC overlay has been provided. So if you just look at the color of the concrete, it is very light. So in that context, here the word white is being used, the white topping pavement. Okay, hot mix asphalt types. There are many different types of flexible pavements. This section covers three of the more common types of hot mix asphalt mix types used. This section provides a brief exposure to dense graded HMA, stone matrix asphalt SMA, and the open graded HMA. So first look at the dense graded HMA. Flexible pavement information in this guide is generally concerned with dense graded HMA. Dense graded HMA is a versatile all-around mix, making it the most common and well understood mix type in the US. So a dense graded mix is a well graded HMA mixture intended for general use. When properly designed and constructed, a dense graded mix is relatively impermeable. Then look at the stone matrix asphalt, and the stone matrix asphalt SMA, although relatively new in the US, has been used in Europe as a surface course for years to support heavy traffic loads and resist studded tire wear. So as far as the stone matrix asphalt is concerned, stone matrix asphalt is a gap graded. It is a gap graded HMA that is designed to maximize deformation or rutting resistance and durability. Then comes the open graded HMA. Well, open graded HMA, this includes both open graded friction course OGFC and asphalt treated permeable materials ATPM. Open graded mixtures are typically used as wearing courses OGFC or underlying drainage layers ATPM because of the special advantages offered by their porosity. So for open graded HMA, we can say that an open graded HMA mixture is designed to be water permeable. Open graded mixtures use only crushed stone or gravel and a small percentage of sands. So here you can see the types of the flexible pavements. This is the dense graded. Dense graded gives the look like this. This is the open graded, and this is the gap graded, and this is basically the SMA. In fact, in SMA we are having stone to stone contact. In SMA we are having, if you just look at this one, the gap graded, we are having the stone on stone contact, and that will greatly reduce the rutting or deformation in the pavement. So this slide is basically meant for stone matrix asphalt, and you can see here the contact between the particles or stones, and you can see here stone on stone contact, and this will greatly reduce the rutting in the pavement. Now again look at the wheel load distribution. We are having the lateral distribution like that, and you can see one thing, that the This is the surface course, this is the base course, and this is the sub-base, and this is the subgrade. Sometimes when the subgrade is of poor quality, then a relatively good materials layer can be provided in between the sub-base and the subgrade. So this is called as the selected layer, which has been provided over here. So this is the typical, you can say, the spread that you are having. One more thing that you can see, that the area over which load is spreading depends on the stiffness of the layer. Higher the stiffness, more will be the area of spread. And you can see this thing even on the next slide. Well, if you just look at this particular slide, this is surfacing, this is base course, this is sub-base, and this is the subgrade. And look at that. The maximum spread you are having in this material, that is the surfacing, and the stiffness of this material is maximum. Or in other words, you can say that this surfacing material, that is the asphalt concrete, this one is superior to base, and the base material is superior to sub-base, and sub-base is superior to subgrade. And look at the wheel load distribution pattern. So what is happening to the angles? There are two ways to understand this. If you just look at the angle theta 1, theta 2 and theta 3, these are the angles with vertical. And you can see that theta 1 is the maximum one. So theta 1 is greater than theta 2 and theta 2 is greater than theta 3. So theta 1 is the maximum one. It is just because of the fact that the stiffness or the modulus of elasticity of this material is maximum. This thing can also be taken in another way, considering the angle with horizontal. Now look at this alpha 1 angle, look at the angle alpha 2 and this angle alpha 3. And you can see here that alpha 1 is the minimum, alpha 1 is the minimum out of the 3. First alpha 1, then alpha 2, and the maximum one is the alpha 3. So basically this is again because of the fact that this is the best material that we are using in the topmost layer, because traffic is moving on this particular layer, so maximum intensity of the loading is in the top part of the pavement. So that's why we use the best possible material at the top. So I will repeat that this material is superior to the base course material is superior to sub-base material, and sub-base is superior to subgrade. And this as a whole is called as the pavement structure. So here you can see the basic components of concrete pavement. So you can see that joints are to be provided. This is the longitudinal joint, and we are having the transverse joints as well. And at the transverse joints, small dowel bars will be provided, and along longitudinal joint, tie bars will be provided. And here you can see the jointed plain concrete pavement. So we are having the plain concrete, but only the steel has been provided at the joints. And this is the top view, and this is the side view. So if you just look at this one, jointed CC pavement, so here in this case of jointed CC pavement, the temperature steel has been provided in the slab of the concrete. So you can see that this is the typical cross section of flexible pavement, and you can see the effect of this field is going up to this depth, and this type of pattern is there. And in the case of rigid pavements, the effect of the load is like this. So pavement comparison. So flexible pavements, multi-layer construction is involved, energy consumption due to transportation of materials, increasing cost of asphalt due to high oil prices. Rigid pavements. So generally we have the single layer structure in the form of concrete slab, and generally last longer, may require asphalt topping due to noise or comfort issues. So heavy vehicles consume less fuel on rigid pavements. Well, if you just look at that, heavy vehicles consume less fuel on rigid pavement, because in the case of flexible pavements you can see that some deformation is there because of the heavy vehicle, but here because of more rigidity the vehicles can be operated without any problem. So that's why the fuel consumption is less in the case of rigid pavement. Rigid pavements are more economical when considering environmental or life cycle costing. Initial cost of the rigid pavement is very high, but if you just consider the environmental or life cycle costing, then you can say that rigid pavements are more economical. Now in this table, a detailed comparison between the flexible and the rigid pavement on the basis of design principle, material, flexural strength, normal loading, excessive loading case, what will happen to the such pavements, stress, design practice, temperature, force of friction, opening to traffic, and surfacing. So look at first one, the design principle. In case of flexible, empirical methods are used based on load distribution characteristics of the components, but in the case of rigid, designed and analyzed by using the elastic theory. So elastic theory concepts are used. Material. Granular materials are used in the flexible pavement, and the rigid pavement, made of cement concrete, either plain, reinforced or pre-stressed concrete. Flexural strength. In case of flexible pavement, low or negligible. In the case of rigid, obviously we are having the considerable flexural strength. Normal loading, the elastic deformation in the case of flexible pavement, and in the rigid you can say it is acting as a beam or cantilever. In the case of excessive loading, local depressions will be there in the case of flexible pavement, and you will be having the formation of cracks in the case of rigid pavement. Stress transmits vertical and compressive stresses to the lower layers in case of flexible pavement, and the case of rigid pavement, tensile stress and temperature stresses are there, and there will be increase in the stresses. Design practice, the flexible pavements are constructed in number of layers, and the rigid pavement is laid in slabs with steel reinforcement. No temperature stress in the case of flexible, but here the stresses are there. In the case of rigid pavement, force of friction is less in the case of flexible pavement, and in the case of rigid pavement it is high. This is basically the force of friction between the particles. Opening to traffic, roads can be used for traffic within 24 hours. In the case of flexible pavement, road cannot be used until 14 days of curing. And as far as the surfacing is concerned, rolling of the surfacing is needed, but the rolling of the surfacing is not needed in the case of rigid pavement. Now you can see the cut and fill sections. This pavement you can see a typical cut section is there, because you can see that this was the original ground surface, but actually the pavement has been constructed in this fashion. This is the top of the pavement. And here look at this one, typical fill section. The original ground surface was this one, and by constructing an embankment, and then the different layers of the pavement have been provided. So this is now the top of the pavement. So this is typical fill section. And if you just look at this one, this is the typical road section cut and fill. So this was the original ground level, and you can see this is in cut and this part is in fill. So pavement responses under loads. So when the wheel load is there, you are having the deformation like this, and you would see that here we will be having the compressive stresses, and here at the bottom of the surfacing we are having the tensile stresses, and then deformation will proceed to the underlying layers of the base and subbase, and ultimately the load will be transferred to the subgrade soil. Three reasons of pavement failures. Number one, deformation or rutting at high temperature as asphalt softens. Number two, fatigue resulting in cracking due to high loads or aging. Number three, low temperature cracks as asphalt becomes brittle and shrinks in cold weather. So asphalt cement is held together by aggregate interlock or internal friction. So here you can see the structure of the asphalt concrete. Gravel has very little internal friction and interlocking, while crushed stone has high interlocking friction. Particles should always be at the surface to provide traction when the surface is wet. Too much asphalt results in segregation of the asphalt and aggregate called bleeding or flushing. Now some points are given in this block. Air pockets account for 2 to 6% of the volume. Aggregates constitute 70 to 75% by volume or 90 to 95% by weight. Excessive amounts of binding material tend to lubricate the particles and lower the stability of the pavement. Well, if you just look at the aggregate grading, first look at the open graded aggregate. So open graded aggregate contains little or no fine aggregate. It has relatively large white space and is good for roads requiring high permeability. So we can say that open graded HMA mixture is designed to be water permeable. So open graded mixes use only crushed stone and small percentage of sands. And we also know that there are two types of open graded HMA mixture. Open graded friction coarse, that is OGFC, and asphalt treated permeable base, that is ATBC. Okay, as far as the dense graded mix is concerned, dense graded mix is a well graded HMA mixture for general use. They can be further classified as either fine graded or coarse graded, or even there is a third category, that is intermediate graded. So in case of dense graded aggregate, when we are saying that it is coarse graded, it means coarse aggregate is dominant. In intermediate graded, more sand is present than the coarse aggregate. In the case of fine graded, more fines and sand than the coarse aggregate. So in this way there are different you can say the categories of the dense graded aggregate. So here if you just look at some description which is given regarding the intermediate graded aggregate, intermediate graded aggregate contains more sand than coarse aggregate. So dense graded aggregate has high fill fraction and slow curing rate. Both coarse and intermediate graded require a seal coat to make them impermeable to water, while dense graded aggregate does not require a seal coat. Well, here the dense graded, this one is basically the fine graded, and in which you are having more fines and sand than the coarse aggregate. So in that particular case we don't require the seal coat, but in the case of coarse graded aggregate and intermediate graded aggregate we need the seal coat. So I will repeat this thing. Coarse graded means coarse aggregate is dominant. Intermediate graded means more sand than the coarse aggregate. And this one, when we are considering simply the dense graded, it means it is the case when more fines and sand than the coarse aggregate. So in that particular case we don't require any seal coat, but the other cases of the coarse graded and the intermediate graded aggregate we need the seal coat. So according to ASTM, coarse aggregate is graded aggregate made up of particles that are retained on number 4 sieve. Fine aggregate almost entirely passes through a number 4 sieve. And you know, fines are those particles that will pass through the sieve number 200. Now look at this one, this figure A, that is for the dense graded aggregate. This is B, this is for the open graded aggregate, and here this is too much fines. That means you can see the too much fines are present in this particular grading. There are two types of asphalt concretes: hot mix, hot laid mixes HMA, and cold mixed, cold laid bituminous mixtures. Hot mixed asphalt cement is aggregate mixed with asphalt, cement, tar or emulsified asphalt. It must be heated to about 300 Fahrenheit prior to mixing. Cold mixed asphalt is aggregate mixed with emulsified asphalt, cutback asphalt or tar and applied at ambient temperature. So here some characteristics are mentioned regarding the hot mix asphalt and the cold mix asphalt. So first look at the hot mix asphalt is durable, resistant to rutting, can sustain high loads and wider temperature. Cold mixed asphalt is made for lighter use, cheaper to apply, good for road repairs and resurfacing. Asphalt pavement is flexible, requires less preparation than concrete pavement, and it can be repaired quickly. It also requires a higher amount of maintenance, periodic surface treatment, and becomes hard and brittle with age and under load. Now here you can see the typical cross section of the flexible pavement. We have already talked about that. So pavement, when you consider upon the subgrade, we are having the subbase course, above that the base course, and then at the top we are having the surface course. The subgrade acts as the foundation and may be stabilized if required. The subbase is made of aggregate, sometimes mixed with lime. The base course supports the wearing surface and may be made of asphalt or untreated aggregate such as crushed stone, gravel, sand or cement. The surface course is the finished asphalt concrete, sometimes topped with a sealant. The base course may be designed to provide good drainage. Now in this particular diagram you can see that this is the base course, and within that drainage system has been provided, and through this drainage system water can be drained. Now look at the various spray applications to pavement include seal coats, sprayed asphalt followed by application of stone or gravel cover. The largest aggregate is never more than twice the size of the smallest. Fog seal is a light application of slow setting emulsified asphalt with or without aggregates. A prime coat is liquid asphalt applied to an untreated foundation layer or subgrade of stabilized soil, gravel or water-bound macadam. A tack coat is a thin coat of bituminous material applied to an existing surface to provide bond between the new construction and the existing surface. A slurry seal is a mixture of slow-setting emulsified asphalt, fine aggregate, mineral filler, and water applied to the pavement without heat. So here you can see that this was the original surface. Upon that we have applied the seal coat. Now at the end you would find some information regarding the perpetual pavements, and this is the typical cross section for the perpetual pavement. Perpetual pavement is a term used to describe a long-lasting structural design, construction, and maintenance concept. A perpetual pavement can last 50 years or more if properly maintained and rehabilitated. As Michael Nunn pointed out in 1998, flexible pavements over a minimum strength are not likely to exhibit structural damage even when subjected to very high traffic flows over long periods of time. He noted that existing pavements over about 370 mm or 14.5 inches should be able to withstand an almost infinite number of axle loads without structural deterioration due to either fatigue cracking or rutting of the subgrade. Deterioration in these thick, strong pavements was observed to initiate in the pavement surface as either top-down cracking or rutting. Further, Almayer et al. In 2000 found that most HMA pavements thicker than about 160 mm, that is 6.3 inches, exhibit only surface-initiated top-down cracking. Therefore, if surface-initiated cracking and rutting can be accounted for before they impact the structural integrity of the pavement life could be greatly increased. Thank you.